Chapter 1, Section 1.4, Functions. Here are the section objectives. First, the definition of a function. A function f from a set A to a set B is a relation that assigns each element x in a set A exactly one element y in set B. How I like to think about functions is they have to be predictable. If you have something in x, you have to know where it goes to y. It cannot have two different y's that attach to the same x. So if I give you an x value, you can tell me a single y that it would be paired with. Here is a good picture of it. It has all your x values over here in the blue box. So you have all these different time of days, and then they relate to some temperature during the day. Now, at two different times during the day, like 3 o'clock and 4 o'clock, it can be the same degrees. But if you give me a certain time of day, I can give you a temperature that it is that day. It's not two different temperatures at the same time. So this is an example of a function. Now, when you talk about functions, we can say the word function and we can represent it in multiple ways. We can talk about it. You can say how the function is related. You could do a table or an ordered pair or a list. You could graph it, or you could have an equation. So here we have a couple tests for functions. It says determine whether the relation represents y as a function of x. So you can have a relation which is any relation of any x's to any y's. A function is just a specific relation that has that predictability. So A is the input x is the number of representatives from a state, and the output is the number of senators. So if I give you some number of representatives from a state, can you tell me for sure the number of senators? Let's see. The verbal description does describe a function regardless of the x value, the y value is always 2. You know how different states have different numbers of representatives, but every state always has 2 senators. So no matter what number you tell me of a number of representatives, I can tell you the y value is always 2. So this is a yes. Here, 2 is paired with 11 and with 10. So that's already a big no, because if you say x equals 2, I could say y is 11 or 10. It's not predictable. Here, this is a function here, and it's a bunch of points. I know it's a function because it passes the vertical line test. Every time you do a vertical line, you only hit 1 point. The reason the vertical line test works is if you go to any x value and look for a point, you only find 1. So at x equals 2, y is 3. It's predictable. At x equals -1, y is 0. At x equals 0, y is -1. So it gives you that predictability. Here's an equation representation. This is, it's a parabola. You can kind of visualize what that looks like. This is a function. Every x value is paired with only one y value. Here's another equation. And one way to, say if it's a function or not is to graph it and take a look. Now, I guess we're getting into function notation. So this is an equation. It represents y as a function of x. If it's a function, one way we can write an equation in function notation is to replace y with f of x. And what that does is it tells you, it names the equation f, it identifies it as a function, and then the x in parentheses tells you that, hey, there's going to be x's in this equation. Here's another function written. F of x says this is a function in terms of x, and then here's the equation. When we deal with function notation, if you're asked for f of negative 1, that means you're going to have to put negative 1 in for x. So like I'd replace x with negative 1 and then evaluate. There's a couple more examples, but that's what function notation is nice for, is it gives you a lot of information in this little, spot. It's a function. We're going to plug in negative 1 for x. We'll also see some functions called piecewise functions. Those are when you have multiple functions on with different domains. So here, how it would read is f of x equals x squared plus 1 if x is less than 0. So you'll only use this function if your input is less than 0. Then we start over. F of x is x minus 1 if, I read the comma as if, x is greater than or equal to 0. So if you have an input that is greater than or equal to 0, then you use the bottom one. You never use them both at the same time. You use them, if something is true. So we'll do each of these. First, f of negative 1. Okay, I like to start over here. Is negative 1 less than 0? Yes, it is. So I'm going to do this top one. I'm going to do, x squared plus 1. So negative 1 squared plus 1, so it's 2. Next up, f of 0. Is it less than 0? No, it is not. Is it greater than or equal to 0? Yes, it is. So I'm going to plug it in the bottom one. And the last one, 1. Is 1 less than 0? No, it's not. Is 1 greater than or equal to 0? Yes, it is. So this one also gets plugged in the bottom. Next up, we'll talk about domain. So a domain is defining which x values you are able to find y values for. So where is the function defined? Depending on the type of function, there will be some, interesting things happening. If you have a rational function or something where you have a fraction happening, and you're looking at, what x's could I plug in? Where is the function defined? Well, oftentimes you can plug in any x value you want. You just can't divide by 0. So if I were looking at something like this, I'd say, I just can't have x be 2 or negative 2, because if it was 2, 2 squared is 4, 4 minus 4, that would make the bottom equal 0. Same with negative 2, that would make the bottom equal 0. So I would say, for this one, the domain excludes all the x values that would result in divide by 0, So this says the implied domain would be I'll highlight it, all real numbers, just not x equals 2 or negative 2. Another way you'll often see that written is real numbers, comma, x not equal to plus or minus 2. It's a little bit more concise way to write that. Now, a different issue comes up when you're talking about radicals. So if you have like a square root function here, you can't square root a negative number. So you need to figure out what x values would work so that when you plug in the x value, you get a positive value so that you can take the square root. So what I like to do is just take whatever's under the square root and say that has to be greater than or equal to 0. When you write that in interval notation, it would look like this. You have a bracket to the left of 0. The bracket here means it includes 0. 0 does work. You can include it, comma, infinity. So it goes all the way up to infinity. All right, so here is some examples we'll do. So find the domain. A domain can be a list of numbers. So here, all the x values would be my domain. It's all of the inputs, or all of the x values of each ordered pair. We already talked about the fraction thing. Here I said it's all real numbers. It just can't be whatever x would make the bottom be 0. So in this case, if you're unsure, you just take the bottom, set it equal to 0, and solve. So if I subtract 5 from both sides, x can't be negative 5. So I said all real numbers. It's just that x can't equal negative 5, and that's how you'd mathematically write that. Part C, it's a volume of a sphere equation. Doesn't matter that it's a sphere or whatever, it's just a regular polynomial. There's no fraction, there's no radical. What could the radius be? Well, in this equation, it could be anything. Because it is an application, we are going to say that a radius can't be a negative number. So I'm just going to say radius has to be greater than 0. It wouldn't be a sphere if the radius was 0, so we'll say the radius has to be greater than 0 to work. And then the last one we've talked about too, if you have a square root function, everything under the square root has to end up as a whole being greater than or equal to 0 to be square rootable. So now I'll subtract 4 from both sides, and this one's a little more complicated than the one we had before, but not a big deal. I'm going to solve for x. I did have to divide by a negative, so I will have to flip my arrow, but x has to be less than or equal to 4/3 in order for it to be defined. I'm going to write that in interval notation, negative infinity to 4/3, bracket, because 4/3 is included because of the equal sign, and that's how I'd write that. Here is the typed out answers. That's my list of x values, all real numbers. X can't be -5. Radius would have to be greater than 0. And then that interval. All right, applications. The dimensions of a container. A person works in the marketing department of a soft drink company. It's experimenting for a new can of iced tea that's slightly narrower and taller than a standard can. We've seen these with like the new drinks that have come out. I feel like they're not the same dimensions as a regular old can of pop, kind of taller and thinner. It says that for the experimental can, the ratio of the height is 4. So write the formula for the can as a function of r, write the formula for the can as a function of h. So we'll go ahead and take a look. Here is the volume formula of a can. If it says write it as a function of r, what we want to do there is only have r's in it. We don't want to have h's in it. So I'm going to go back up here and see what my ratio is. It says the ratio of the height to the radius, so height over radius is going to equal 4. So height over radius is 4/1. If I do cross products are equal, that means h equals 4r. So if I want it to be a function of r, I want h out of there, I'm going to substitute out h for 4r. And if I simplify, I end up with 4 pi r cubed. It also says write it as a function of h. Okay, well, if I want a function of h, that means I can only have h's in it. I got to substitute out r. So I'm going to go back up here, and I'm going to solve for r. So r equals h over 4. So then I can go and I can take r out, and I can sub in h over 4. And then I'll simplify. Here I'd have to distribute the squared. It's a little bit more work on this one. So it'll be h squared over 16. And so I end up with h cubed, and I'm going to slip my divide by 16 in with my pi. And then here we can see the typed out solutions. Next is the difference quotient. When you work your way up to calculus, if you end up kind of moving on in the sequence of math classes, this is a difference quotient that, pops up often when you're looking at slope and things. And so it's just a formula called a difference quotient. And what we do in college algebra is just practice using it, practice simplifying. Here it says we have a function, f of x equals x squared minus 4x plus 7, and it asks us to find the difference quotient. So what that would be is First f of x plus h is taking the function and plugging in x plus h. Then f of x is taking the function and just plugging in x for x, or just copying it, and then divide by h. So my whole equation applied to my function is here. This is simplifying, simplify, simplify, until you finally get to the end. Here's a summary of our function terminology. We've gone through all of these throughout the lesson, and that's it.